Today's lesson focuses on trying to explain the difference between the velocity of sound and the frequency of the waves that the sound produces. A common mistake is made when they get the two confused. Now, recall that the speed of sound can be calculated if you know the frequency and the wavelength. Speed of sound is equal to frequency times wavelength. Well, how fast the waves are moving is the velocity of sound, which is commonly mistaken by how often the waves occur, which would be frequency. And so you have to be careful when you're describing truly the speed of sound compared to or the frequency at which the sound waves are being produced. Remember, the frequency is talking about how many compressions and refractions we have in a set time frame, not how fast they're moving through the medium. Now, one of the properties that we're going to look at very specifically is resonance. So, in order for me to describe resonance, we need to understand that when we hear a sound, it's because particles are vibrating enough to cause our eardrums to pick up those vibrations, such as with the tuning forks that we were using earlier in our lessons today. Now, if I can take the tuning fork as we saw and strike it without any other thing, without it affecting, any other thing, we really can't hear the sound of this tuning fork. So even if I strike it, it's very minimal. But if I put it against some other material and it transfers its vibration to the other material, we may be able to hear that sound. The reason being is because we can get one object vibrating at the second object's what we call natural frequency. If the second object starts vibrating as well as the first object, it's going to force that second object into vibration. So if we have exactly the right frequency, it can actually make the second object shatter because all the particles are moving exactly at the same rate with the same frequency, that it's too much for the material and it just breaks apart. It just blows up. Now, a common use of resonance, which means in the Latin resound or sound out loud, is used in sound production of musical instruments. Now, the reason why this is a phenomenon that we have with musical instruments is because as a disturbance is made and it's causing this what we call wave train, a consistent movement of waves in and out. It is by the reflection of the waves. So as the wave is produced or the sound is produced, it travels through the object, hits a barrier, and then comes back, which is what reflection is, an echo in common terms. And so as this echo occurs, the sound is shut out and it bounces off a barrier and comes back. We have these two waves meeting because this sound over here is traveling this way and this one is traveling towards it, which causes superposition. Remember constructive interference that we had already discussed as well. And this in turn amplifies the sound. So if we have, like I have over here, this simple drawing of a cylinder that's with air with a tuning fork on top of it, as the vibrations of the tuning fork affect the air inside the cylinder, it hits this boundary down here, which is like a node, and it reflects back up here. And this continual movement is what causes eventually all the particles to vibrate at the same rate so that we can hear the sound. Now, I can do this without air as long as I have something that's going to literally vibrate as well, like with the tuning fork. So here's a demonstration that I can give you. If I hit my tuning fork and put it against here, you can start picking up the sound because it's making the board itself vibrate as well. So here it goes again. Let me see if I can get it louder. And so as I do this, I can actually amplify it. Now, because there isn't any air, it's harder for me to get the material of my board to vibrate as well so you can hear it. Even though it does travel faster in a solid material, our ears can't really pick up those vibrations. But if I get a guitar, not that I'm going to bust out playing the guitar, I'm going to show you what happens with a tuning fork as I put it on the box of the guitar, which obviously has a hole and it's filled with air. Now the material of the guitar itself also is a little bit easier to move than my board back here. So again, I can strike it and put it on the guitar, and we can actually amplify that sound simply because now we have a more narrow space in which to affect the vibrations and have that continual reflection, interference, and then reflection, and so it's bouncing back and forth, such as what we call the wave train. Now, if you were just to take a simple string and put it out and pluck it, you wouldn't hear it. You really need the whole mechanism of the guitar. And the length of these guitars have a lot to do with what sounds they produce. A bass guitar is going to be a lot longer because if we extend the air requirements, we can change the pitch to a lower pitch, meaning, and as well as the strings. So there is a difference in the size of the guitar itself in order for us to get the appropriate sound. Now, a smaller guitar would have a higher pitch, such as a ukulele. So we have differences in how our guitars are structured, simply because that's going to give us the different pitches and the compliments that we get when we hear all those mariachis out there singing their lovely songs. Now, if you can get a material, say this was made out of glass and the tuning fork touches the glass, it can actually make the glass itself, not just the air, but the glass piece itself, vibrate with so much energy that it causes it to shatter. So this is our basic idea of resonance. It is really is caused by one object vibrating at the second object's natural frequency. Key to that here, forcing the second object to vibrate into vibrational motion.